Hi everyone! Today, as the title shows, we're going to share the design and implementation of voltage to current converter. First of all, we prepare our schematic design on Proteus.
So now I'm going to present our circuit, which is a voltage to current converter. Let's start with the first block. So we have a voltage of 18 volts as an input voltage. We also use two regulators, one to provide 10 volts. This regulator is called 78 and 10. And the second regulator is to provide 12 volts to supply our transistor and our operational amplifier LM358. Also, we use capacitors for two capacitors for each regulator to reduce noise and to provide stabilized voltage. So for our next block, we used a voltage divider by R1, the two resistors R1 and R2. So we used a voltage divider because the operational amplifier, which is LM358, functions better with low voltage. Our next block is offset adjustment. For this block, we used a potentiometer of 10 kilo ohm, which is called RV1. We also use a resistor relay to this potentiometer, which is called R6. So this resistor is used to not disturb the voltage. Our next block is operational amplifier control block. So this amplifier, which is called LM368, is used as a comparator or a controller. So it compares two voltages, the input voltage, which comes from the potentiometer, also the feedback voltage, which comes from the output. So based on this comparison, it adjusts its output to keep the system stable. So next is feedback network. The potentiometer, the second potentiometer RV2 and the resistor R6 form the feedback loop. So this feedback is really important because it stabilizes the output and it ensures accurate current control. This is what makes the system precise. So the last block is the transistor stage, which is our most important block, because in this block the voltage will be converted into current. The transistor BC547 acts as a current controller. So the operational amplifier LM368, its output goes through this resistor, which is called R3, to control the base of the transistor. The transistor then regulates the current flowing through the load. In simple terms, the transistor converts the voltage signal into controlled current. After explaining the importance of each block, now it's time to test our circuit. So as you can see, for 0 volts, we obtain 4 milliamperes. We can also test if our circuit works by doing a simple equation, which is the rule of Ohm. Here, as you can see, we obtained 1.27 volts. If you divide this by 220 ohm, we obtain around 4 milliamperes. For 10 volts, as you can see here, we obtained 20 milliamperes. And for 0.75 divided by 220, we obtain 20 amperes. This is the law of Ohm.
In the second step, we move to the circuit implementation on a breadboard. This stage is crucial for validating our design before finalizing the PCB. As you can see, when we apply 0 volt, we obtain approximately 4 milliamperes by adjusting the potentiometer to set our baseline. However, when we switch to 10 volt, the output currently reaches 17 milliamperes. In the last step, to fabricate our custom PCB, we use the toner transfer method. The process begins by printing the PCB layout designed in EasyEDI using a laser printer on glossy paper. Since laser toner is plastic-based, it can be transferred to metal surfaces using heat. We then place the printed layout onto a copper-clad board and apply the heat using standard iron. The heat caused the toner to stick to the copper, forming the circuit pattern. Next, we submerge the board in a ferric chloride solution. This chemical selectively etched away the exposed copper, leaving only the areas protected by toner. After etching, we rinse the board with water and cleaned off the remaining toner to reveal the final copper traces. The last step involved drilling holes at component locations using a fine drill. This prepared the board for soldering and final assembly. Finally, we soldered our component using soldering iron and solder, and the printed circuit board is ready. Be careful before powering up, ensure there are no short circuits by performing a continuity test with a multimeter. And for the functional test, we measure the voltage across resistor R5 to achieve a base current of 4 milliamperes. The measured voltage should be 1 volt. Upon pressing the switch, the voltage increases to 446 volt, which corresponds to a current of 17 milliamperes. And that's it. Thanks for watching.